Hello and welcome to section 2.3. Let's get started looking at this. In section 2.3, we're going to learn the precise definition of a limit. So this is a more formal way of talking about limits and how they come to be. So overall, what we're going to be doing here is we're going to clarify some terms that we've been using all chapter. We are clarifying what it means, for instance, to say x approaches a certain value. Okay, so approaches, which is kind of a vague term. What does it mean to approach something? Well, we have an idea of what that means in a normal sense, but we're going to talk about it in a more mathematical sense here. This is also kind of clarifying what it means to get near a certain value or to be close to a certain value. So we might say like, oh, as x approaches c, f of x gets close to L. So we're going to see what those terms really mean. All right. So the big idea here is that if we are within some target distance of x equals c on the x-axis, we are guaranteed to be within a corresponding certain distance of L along the y-axis. Okay, let's draw a picture. So here's our x-axis, here's our y-axis, or f of x along there. So let's draw in a function, f of x. Nothing too crazy here. Let's give it a little hole in the graph, perhaps. And something like that'll do. Okay, let's say we want to look at the limit of this function as x approaches c. Okay, so we could see just from what we know of limits that we would normally say, okay, we put our fingers on the graph and we come in from both sides, come in towards C, and we would say that the limit is going to be this y value right here. So that's going to be our limit L. We know that. Okay. But what we're going to look at now with this idea, this new idea, is that we're going to be within some target distance of x equals c on the x-axis. Okay, so around x equals c, we're going to mark off a little margin, like from here to here or so. Okay. And we're going to say we've gone out some little distance away from C in either direction there. Okay, so that tiny little distance, I'll zoom way in here. This little distance away from C, we call that delta. And that's a Greek letter, that's lowercase delta. Okay, so if that distance is delta, then this mark right here on the x-axis is going to be c plus delta. And then this little mark over here, we've gone, to the other side of c by that same amount. That would be c minus delta. Okay, so we're going to say that we've hit within that target distance delta. Okay, that is delta. So we're within delta of x equals c on the x-axis. Now, if our x value is somewhere in there, we are guaranteed to be within a corresponding distance of L along the y-axis. So let's see what that looks like here. Take up the edges of those margins. Okay. Now let's see here. We'll go over and look at the corresponding y values. Okay. And we can see that doing this creates a little margin or a little area around L, y equals L. Okay, just like we were doing for doing down on the x-axis here, we have a situation that looks like that on the y-axis now. So this little distance in the y direction, we are going to call that epsilon. Okay. So we would have L plus epsilon and L minus epsilon bordering that region along the y-axis. Okay, so yeah, our idea here is that if we are within that target distance delta of x equals c, we are guaranteed to be within the corresponding certain distance epsilon. Okay, epsilon. We're within that distance of L along the y-axis. So as long as your x value is somewhere in here, that means the y value you get will be somewhere in this interval. Okay, so let's add that little detail. Okay, as long as you have x in here, that will mean that f of x is in here, in that region. Okay, so one of those things leads to the other. Now, what does that mean for our limits? Well, that means if we can define delta and epsilon that go along with each other, we can bring in that interval or that region around x equals c to be as small as we want it to be. Okay, we can get very, very close. There's that word again, closeness. We can get very close to x equals c, and that will correspond to getting very, very close to y equals L, or f of x equals L. Okay, so that's how this is going to correspond to our limits there. Now, this goes with the official definition of a limit. We say that the limit as x approaches c of f of x equals L if for every number epsilon that is greater than 0, there is a number delta also greater than 0, such that f of x minus L in absolute value is less than epsilon whenever the absolute value of x minus c is less than delta. Okay, now this statement might look a little intimidating at first, but it really goes right along with the picture that we just drew. So the thing to remember here is that absolute values simply represent distances. So what we're looking at with this first part of the definition here, the absolute value of f of x minus L, that is just the distance between f of x and L. So distance between f of x and L is less than epsilon. Okay, that just is a mathematical way of saying f of x is in this region. Okay, so the distance between f of x and L is less than epsilon. That means f of x has to be somewhere in here. All right. And then our other part of the definition, whenever absolute value of x minus c is less than delta, that absolute value is just expressing the difference or the distance between x and c. Distance between, between x and c is less than delta. So that is just saying that your x value is somewhere in here, all right? Within a distance delta from c. Okay, so x is in here, means f of x is in here. All right, that's all the definition is saying.